In this video, we're going to quickly consider the Carnot cycle for a calorically perfect ideal gas as the working fluid. So Carnot cycles are kind of hard to draw at first. You have two shallow curves and two steeper curves. The shallow curves are, of course, our isotherms where n equals 1. They're polytropes of n equals 1. So this guy we could label as TH. This guy we'll label as TL, so high temperature and low temperature isotherms. The side adiabats have n equal to k, and we acknowledge that by using insulation double hashed lines. So we go around this cycle from 1 to 2 to 3 to 4, typically in a clockwise motion if we're talking about an engine. We saw in class that we expect there to be heat in at the high side, the high temperature side, whereas heat flows out from the low temperature side. We're also given that the area, of course, is the work of the cycle, which is equal to the heat of the cycle by the first law of thermodynamics. Of course, this is in the PV plane. So this is a general idea for a Carnot cycle with a calorically perfect ideal gas as the working fluid. So in order to kind of take a look at this problem in the concrete, we consider a case where TH is 400, TL is 300 Kelvin. V1 is known, little v1 is just 0.4 meters cubed per kilogram, and little v2 is 1 meter cubed per kilogram. And we are also told to consider that our calorically perfect ideal gas here is going to be air, and we've also been told that there's only 1 kilogram of it. So this is our problem as it's been given to us, and we'd like to find in this kind of a problem, typically we want to find the work of the cycle, or the heat of the cycle, and we're going to want to find, in this case, besides the work of the cycle, the heat transfer from the two sources at the hot and low temperatures. So that's what we want to find. Our governing equations, they're going to contain the things we want. So of course we want the work of the cycle, it's equal to the heat of the cycle. That's the first law written down for cycles. We also have U beta minus U alpha equals Q alpha to beta minus W alpha to beta. This is the first law for processes, so the change in energy equals the heat in minus the work done. We also can recognize that we're probably going to have to use some kind of equation of state here. If I'm given 2, I want to get the rest for free. So the EOS's are going to be given for the substance gas, for the substance air and the phase gas. Usually I write these backwards. And since we have gassy air, let's use a calorically perfect ideal assumption. So we're going to have the PV equals RT. This is obviously the ideal gas law. And then we're also going to have that du equals CV dt, where this is a constant. And this is the calorically perfect part. So when we write down CPIG, we get 2 equations of state, not just one. We get a thermal equation and a caloric equation. And then lastly, really to connect all of these things, I can see that I know everything at 1 and everything at 2, but 3 and 4 I seem to only know the temperature. So let's go ahead and write that down. So at 1, I know TH is the temperature and V1 is given. I can find P1 quite easily and U1 from this. At 2, I know the temperature and the volume again. At 3, I just know the volume, or I just know the temperature right now. And similarly at 4, I just know the temperature. So if I want to find more information, it's going to come about by connecting these states. in the cycle. So obviously the connection from 1 to 2 and 3 to 4 is that T is a constant. So n equals 1, n equals 1, whereas from 2 to 3 I have adiabats, where n equals k for both of those guys. So I need to connect 2 to 3. I know everything at 2. To get more information at 3, I need to connect 3 to something that, well, that I don't know. I don't know, I'm sorry, something that I do know, and that would be state 2. And what connects them? The polytrope. So let's consider isotherms real quick. That's 1 to 2. It's also 3 to 4. So we know for this case that temperature is a constant. In other words, PV to the alpha equals PV to the beta, or PV at beta. For any state on these isotherms, P times V is a constant on this isotherm. P times V is a different constant on this isotherm. This is a polytrope with n equal to 1. Right? This is obviously the case. If temperature is a constant, then P times V is a constant, and we're done with this. The work equation is a polytrope with n equal to 1, which we usually write down as P times V at a given value of alpha, say for instance, times ln of beta, V beta over V alpha. It's maybe a little bit more useful to realize that P times V is just going to be MRT. So MRT, where T is either TH or TL, times ln of VB over V alpha. And this is helpful because we know the temperatures easily, and this lets us compute some work terms quickly, even just the temperatures. What else do we know? We are going to be able to write down U beta minus U alpha. That would just be the integral of m du from alpha to beta. Of course, m is a constant, so it comes right out front. Integral of du is u beta minus u alpha multiplied by n, giving me big U. I have the extra extensive properties. Or du is just mcv dt from alpha to beta. So m and cv are both constants for a calorically perfect ideal gas. The integral of dt is t, so I'm going to get mcv t beta minus t alpha. Of course, in this case, dt is 0. T beta is T alpha, so this is a goose egg for the isotherms, and that tells us that on isotherms the gas doesn't get hotter, and so its thermal energy doesn't go up. Its thermal energy remains a constant. What does this mean in terms of the first law? So in terms of the first law, I got U beta minus U alpha equals Q alpha to beta minus W alpha to beta. This vanishes identically. Work alpha to beta is an equation that I know, and so let's write it down. Q alpha to beta therefore is the work from alpha to beta from the first law, and then the definition of work comes in MRT ln V beta over V alpha. And this is pretty much the summary of what I know about isotherms for the calorically perfect ideal gas in the Carnot cycle. Let's talk about the adiabats. So the adiabats are 2 to 3 and 4 to 1. What am I going to be able to do with these guys? I know that PV to the K is a, oops, PV to the K is a constant on these guys. And this can be easily rewritten substituting for P equals RT on V, or MRT on V. I can rewrite these guys as simply TV to the K minus 1 at alpha equals TV to the K minus 1 at beta. And this is useful. I know temperatures at on every area or every point, so this is an easy guide to use. In fact, I know, for instance, from 2 to 3, I know everything at 2. Everything at 2 at 3, the only thing I need to find is v. So I could solve this for v. So say v beta here is going to basically be equal to v alpha times t alpha on t beta all over 1 to the k minus 1 power. And that lets me solve for my unknown volumes in terms of this ratio here. In fact, you can kind of see here before we go that v beta over v alpha is given by the ratio of temperatures. So it's interesting. The temperatures between 2 and 3, this ratio is the same as the temperature ratio between 1 and 4. In other words, we could write down from this guy pretty much right away that V3 over V2 is equal to V4 over V1. So that's pretty helpful information, since these are isotherms connecting 1 and 2 and 4 and 3. And we'll find that it helps us in a minute. What else do we got here? This is just the process equation. Let's talk about the work. The work from alpha to beta is going to be PV to the beta minus PV to the alpha, or PV at alpha, all over 1 minus n. N is k in this case. PV, of course, is just MRT. So I could write this down as MR on 1 minus k times T beta minus T alpha. So this gives me the work just in terms of the temperature differences. And the temperature differences on the isotherms are the same, aren't they? So for instance, T3 minus T2, that gives me the work from 2 to 3. Well, the work from 4 to 1 is MR K minus 1, T1 minus T4, well, that's the same thing. It's just TH minus TL. In fact, I could write that down very quickly. So work from 2 to 3 is MR 1 minus K TL minus T, sorry, TL minus TH. And this number is actually, so this is a negative number, isn't it? TL minus TH is a negative number, but 1 minus K, K is larger than 1, it's the ratio of specific heats. So this is actually a positive number. Interestingly then, work 4 to 1 is going to be equal to MR on 1 minus K times TH now minus TL. And, well, this is just minus work 2 to 3. And this is going to be less than 0. So the work going from 4 to 1 around this cycle is volume gets smaller, the work is negative. So we can see that the works done on either one of these are actually the same, just opposite in sign. So let's we've considered the process, we've considered the work. Now let's consider the first law briefly. So the first law would give us that U beta minus U alpha equals Q alpha to beta minus W alpha to beta. In this case, we've found that U alpha to beta, or I'm sorry, U beta minus U alpha is just CV T beta minus T alpha. It's the same exact equation as before integrating, but now beta and alpha are different numbers. Let's throw this into a different form real quick. So we know something about CV. CP equals CV plus R. This is Meyer's relation as we learned in class. So if I wanted to, let's rewrite this very briefly. So CP on CV equals 1 plus R, and this is just K. So I would be able to say that, okay, k minus 1, or I'm sorry, 1 minus k would be equal to, this should be on CV. 1 minus k is going to be equal to minus r on CV. Or we could say that CV is just going to be equal to minus r on 1 minus k. So I could write down this interesting equation, u beta minus u alpha equals minus r 1 minus k t beta minus t alpha. Let's plug this stuff in. So we're going to plug this in for this guy. So it's going to be minus r 1 minus k t beta minus t alpha equals q alpha to beta. And what's w alpha to beta? W alpha to beta, as we found before, is just mr over 1 minus k. Let's go ahead and plug that in. So, forgot the m here. Minus mr on 1 minus k t beta minus t alpha. Well, these are the same term. They cancel. Q alpha to beta equals 0. That's what we knew it had to be, right? We knew that on a polytrope there is no heat transfer. So, lastly, we want to find the work of the cycle. We could do this by adding up the works. All of these are non-zero numbers, but as we saw before, work 4 to 1 is just minus work 2 to 3. So when I add those two guys up, 2 to 3 and 4 to 1 cancel with one another. So they're all non-zero numbers, but it might be easier to think about the work of the cycle in terms of the heat of the cycle, which is just Q1 to 2 plus Q3 to 4. Why? Because Q2 to 3 and Q4 to 1 are both 0. So we could do it this way, and we furthermore know that work 1 to 2 is Q2 to 3, and that work 3 to 4 is Q3 to 4. So these are, all of this is working together. We can use either one of these equations. Let's just plug in for what we know here. The works are mRTH from 1 to 2 times ln of V2 over V1 minus, or I'm sorry, plus mRTL ln of V4 over V3. Well, we can actually throw this into a separate equation pretty quickly. We can do that using this guy from our previous sheet. So we actually know that, for instance, from this guy right here, that if I just cross divide, or that V4 over V3, that's going to be equal to V1 over V2, which is minus so let's plug that in. So this guy here is really just V1 over V2. Well, this is just V2 over V1 to the minus 1. So I'm going to have that the work of the cycle now would be mR times TH ln of V2 over V1 plus TL of ln of V2 over V1 minus 1. Well, the minus 1 can come down, rule of logarithms, and I'm going to have then mR ln V2 over V1 times TH minus TL. And of course, this is exactly what I'm given in my problem statement. I'm given the temperatures and I'm given the volumes. And that's how we can do this problem.